MathKlik.
Mabuhay! What are zeros of quadratic function? How do we find the zeros of a quadratic function? How are the zeros of quadratic function interpreted geometrically? In this lesson, we will discuss how to determine the zeros of quadratic functions. The parabolic structure allows the graph of a quadratic function to intersect the x-axis in three different ways. The parabola may cross the x-axis once. It may cross the x-axis twice, or it may not cross the x-axis at all. If a parabola intersects the x-axis, the ordinates of the points of intersection is 0. That is why the abscissas of the point of intersection of the parabola and the x-axis, where the ordinate is 0, is called the zeros of the quadratic function. The zeros of a quadratic function f are the values of x such that f of x is equal to 0. So, if a quadratic function is defined by f of x is equal to ax squared plus bx plus c, the zeros of f of x are the roots of the corresponding quadratic equation ax squared plus bx plus c is equal to 0. Since the zeros of a quadratic function are directly associated to the roots of the corresponding function, I suggest that you master how to solve quadratic equations either by factoring, completing the square, or using the quadratic formula. Let's do some exercises in finding the zeros of quadratic functions. Find the zeros of f of x is equal to x squared plus 7x plus 10 using factoring method. First, write the corresponding quadratic equation. Factor the left side. The factored form is quantity x plus 2 times the quantity x plus 5 is equal to 0. Solve for x by equating each linear factor to 0. The roots of the equation x squared plus 7x plus 10 is equal to 0 are x is equal to negative 2 or x is equal to negative 5. Therefore, the zeros of the quadratic function f of x is equal to x squared plus 7x plus 10 are negative 2 and negative 5. Here is the graph of f of x to see the geometric interpretation of its zeros. Take a look at the points marked red in the graph. Let's take another example. Find the zeros of the quadratic function g of x is equal to negative 2x squared plus 3x plus 5 using the method of completing the square. First, write the corresponding quadratic equation. Divide both sides of the equation by negative 2 to make a equals 1. Then, add and at the same time subtract 1/2 the coefficient of x, which is negative 3 over 2, and then square it. You should get 9 over 16. Factor the PST and then combine the fractions. Add 31 over 16 to both sides. Apply the square root property. Then solve for x. Therefore, the zeros of the function g of x is equal to negative 2x squared plus 3x plus 5 are 3 plus square root of 31 over 4, which is approximately equal to 2.14, and 3 minus square root of 31 over 4, which is approximately equal to negative 0.64. Here is how g of x looks graphically. For our next example, let's find the zeros of the quadratic function h of x is equal to x squared minus 2 using the quadratic formula. First, write the corresponding quadratic equation. Use the quadratic formula to find the roots of x squared minus 2 is equal to 0. That means we need the values of a, b, and c. The value of a is 1, b is 0, and c is negative 2. Substitute these values to the formula and simplify the resulting numerical expression. Therefore, the zeros of h of x are square root of 2 and negative square root of 2. And the points square root of 2 comma 0 and negative square root of 2 comma 0 are the points on the graph of h of x that are on the x-axis. Here's the graph of h of x. The definition and characteristics of a quadratic function and the nature of its roots of the corresponding equation will be helpful in deriving functions as well as quadratic equations. Let's demonstrate this. Derive the quadratic function f of x with vertex negative 1, 4 and zeros negative 3, 0 and 1, 0. The coordinates of the vertex is given, so let's use the vertex form of the quadratic function in deriving f of x. Substitute the coordinates of the vertex to the vertex form. Then, take the coordinates 1, 0. That's one of the zeros of f of x. Substitute this to our equation. The result is an equation containing the unknown a. And solving this equation for a gives a is equal to negative 1. This implies that the graph of f of x opens downward. Now, substitute a is equal to negative 1 to the vertex form, which is the same as f of x is equal to a quantity x plus 1 quantity squared plus 4. Expand and combine similar terms. Therefore, f of x, the required function, is equal to negative x squared minus 2x plus 3. Recall that the zeros of a quadratic function are also the roots of the corresponding quadratic equation. Let's solve this. Derive the quadratic function g of x with 2i as one of its zeros. Recall the meaning of complex conjugates. If 2i is a root of an equation, its conjugate negative 2i is also a root of that equation. So, to derive the quadratic function with zeros 2i and negative 2i, let's use 2i and negative 2i to form the corresponding quadratic equation. Remember, the imaginary number I, by definition, is a number whose square is equal to negative 1. Let's use this a bit of information in solving the equation quantity x minus 2i times x plus 2i is equal to 0. Find the product of this sum and difference. This gives us x squared minus the quantity 2i plus quantity squared is equal to 0. Simplify this equation by applying the definition of imaginary number. The result is x squared minus 4i squared is equal to 0, or x squared plus 4 is equal to 0. Therefore, the quadratic function with zeros 2i and negative 2i is g of x is equal to x squared plus 4. Let's solve this. Find the quadratic function h of x whose graph passes through the points negative 1, 0, 0, 0, and negative 3, 6. The required function is of the form h of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Every point on the graph of h of x satisfies the given function. This implies that we can replace x with the abscissa negative 1 and h of x with the ordinate 0 to form our first equation. 0 is equal to a quantity negative 1 squared plus b quantity negative 1 plus c, which when simplified is equivalent to a minus b plus c is equal to 0. Similarly, we can replace x with the abscissa 0 and h of x with the ordinate 0 to form our second equation. 0 is equal to a quantity 0 squared plus b quantity 0 plus c, which when simplified is equivalent to c is equal to 0. Also, we can replace x with the abscissa negative 3 and h of x with ordinate 6 to form our third equation. 6 is equal to a quantity negative 3 squared plus b quantity negative 3 plus c, which when simplified is equivalent to 9a minus 3b plus c is equal to 6. Of the three equations formed, c is equal to 0 is very clear. Let's use this value to further simplify equation 1. If we replace c with 0, equation 1 becomes a minus b is equal to 0, or equivalently, a is equal to b. Replace also the c in equation 3 with 0 to form the equation 9a minus 3b is equal to 6. Since a is equal to b, then 9a minus 3b is equal to 6, which is the same as 6a is equal to 6 or a is equal to 1. And therefore, b is also equal to 1. We can now use the values a is equal to 1, b is equal to 1, and c is equal to c to write the required quadratic function h of x. Therefore, h of x is equal to x squared plus x. Now, try this. Find the zeros of q of x is equal to 12x squared plus 23x plus 5. You can use any method, but take note that 12x squared plus 23x plus 5 is factorable. Its factors are 4x plus 1 times 3x plus 5, and its roots are negative 1/4 and negative 5/3, which are also the zeros of q of x. Determine the quadratic function p of x with square root of 2 as one of its zeros. If square root of 2 is one of the zeros of p of x, then negative square root of 2 is also a zero. They are quadratic surds. This means p of x is equal to quantity x minus square root of 2 times quantity x plus square root of 2, which is equal to x squared minus 2. For more matitinig tips, just click MathKlik. And please, don't forget to subscribe and click the notification bell for our next video lesson. See ya!